So welcome back. In the second half of today's course session, we are going to work some more with non-deterministic finite automata, and we are going to explore in more detail what is the relationship between non-deterministic finite automata and deterministic finite automata. And this relates to the question that one of your colleagues asked at the end of the first part of this course session, namely, are NFAs always somehow translatable into DFAs? Or are there things that NFAs can do that DFAs cannot do? And what I mean by saying, are there things that NFAs can do that DFAs cannot do, is precisely, are there languages that NFAs can accept, but for which there is no DFA that accepts them? These are all natural questions, fundamental questions, that have been answered, fortunately for us, by people a while back. So that's a question in a different formulation. What is the power of magic? Does the possible use of magic in automata, in finite automata, bias something? Well, in fact, it doesn't bias anything. What does this mean? DFAs and NFAs both accept the same class of languages. And this is the collection of regular languages. In other words, every time you have a language that can be accepted by a DFA, there is an NFA that can accept it. Every time you have an NFA, there is an equivalent DFA that accepts the same language accepted by the DFA, the NFA that you started from. Okay, the question is, what about the one that you were showing us before? B's, for instance, all the strings that had a B with as the fourth symbol from the right. Well, I didn't say for that language that there was no DFA that accepts it. What I said was that there is no DFA with fewer than 16 states that accepts it. This is different. Here we are disregarding the size of this automata. We are just focusing on, does there exist one? Is there a DFA that does the job that DFA does? And the answer, as this theorem says, is always yes. In fact, we are computer scientists. Computer scientists, unlike mathematicians, are not satisfied with the existence proof. Yes, there is a DFA that does the job of an NFA that somebody gave you. What we want to do is to construct this thing. And in fact, even better than that, what we want to have is an algorithm, a mechanical process for constructing the DFA from an NFA. This algorithm is nothing but a compiler, if you wish, that takes as source language NFAs and outputs as target language DFAs. And the correctness criterion is the DFA that the compiler spits out should accept the same language that the input NFA should accept. And in fact, there is such an algorithm, and it's called the subset construction. It's a piece of classic theoretical computer science. In fact, not just a theory, it's also used in practice in optimized forms. Now, why is this algorithm called the subset construction? Well, let's see. Let's try to think how we could actually go about simulating deterministically the behavior of a non-deterministic automaton. And now I ride my luck and try to interact with this non-deterministic machine, because it's behaving non-deterministically today. Okay, so what we want is an NFA to DFA converter. DFA, so, oh no, sorry, NFA, NFA to DFA. The other bit is easy because a DFA is an NFA that doesn't use magic. There's nothing to do. Okay, so what we want is something that takes as input a machine M, which is an NFA, and spits out a machine N, which is a DFA. Okay, what is the relationship? The relationship is that the language accepted by M, the NFA, should be exactly the same as the language accepted by N, the target code of the translation. Okay, make no mistake, the algorithm that we are going to give is a compiler. Well, it's a special compiler because the input and the target language are graphical languages. They're automata, but it's a compiler of sorts. Okay, so how does this work? As usual, before giving the general idea of the construction, let's look at an example. So let's assume that our input NFA would be the one that we've been looking at for a while, namely the NFA that accepts the set of recognized die. Okay, I'm pretty nervous today, but I'm doing my best to keep my cool on this one. Okay, so this is my input. This is M. And let's give names to these two states because we are going to use them. Okay, so how can we deterministically simulate the behavior of this NFA? Well, remember, when I showed you the behavior of this automaton on an input string, I drew a tree of possibilities. So, for instance, after this automaton had read an input symbol, say the input symbol A, it could be in any of the states which were at the first level in the hierarchy of this tree. So by reading an input symbol, we could be in one of a set of states. We could be either in S0 or in S1 by reading an A starting from S0. So if you wanted to deterministically decide what this automaton can do, it sounds like it might be a good idea to use it as a data structure, a set of states. These are the set of possible states that the NFA could be in after having read some fragment of the input string. So why don't we do that? In the beginning, we are in the start state, and there is only one. So we are in the set that the set of possible states initially contains only the start state. Now, if I am in the start state and I read an A, afterwards I can be either in S0 or in S1. So we remember this fact by considering a set with these two states. And we connect the start state to this new set with two states by the input symbol that brought us there. Okay, so how do we read this? I initially am in the start state. If I read an A in the start state, I go to either S0 or S1. And I remember my possibilities by considering the set of all these possibilities. If instead I am in the initial state S0 and I read the B, where can I go next? Only to S0. So I have a loop here. So far, so good. We have figured out all the possible behaviors of the NFA from the start state. Now let's look at what happens if I'm in state S0, S1. Now this is a set of, this will be a state in my DFA that simulates the NFA. Okay, so what happens if I am either in S0 or in S1 and I read B, say? Okay, where can I go next? Okay, remember, I'm either in S0 or in S1. I read B, so the places where I can possibly go are those that I can reach if I were in S0 and I read B, plus those that I could reach if I were in S1 and I read B. I need to account for all the possibilities because I don't have magic anymore. I need to be deterministic. I need to look at all the possibilities and remember them all. Okay, so if I am in S0 and I read the B, I can only go to S0. If I'm in S1 and I read the B, I can go nowhere. So where is it that I go if I'm either in S0 or in S1 and I read the B? You go back to S0, the state that only contains S0. If I'm instead in S0 or in S1 and I read an A, where do I go? Okay, so if I'm in S0 and I read an A, afterwards I can be either in S0 or in S1. And these are actually all of the places where I can be because there are only two states. In fact, from S1 I go nowhere. So it wouldn't add anything anyway, but I cannot add anything anyway because already from S0 I can go anywhere by reading an A. So what I have is a self loop here. Okay, so far so good. That's the deterministic automaton. But we need to decide what is the start state. That's easy. It's the state that only contains the start state and nothing else. Now, what is or are the accept states? Okay, in the original NFA, there was only one accept state, and that was S1. Okay, this points to the fact that our accept state here should be this one. Why? In fact, in general, any state, any set of states that contains some accept state should be an accept state of the DFA that you spit out. Why? Because remember, we accept an input string if there is a way of doing it right, of processing it right, which means that we land in, at the end of the, having read the whole input string, we land in some accept state. So any set of states that contains some accept state is a possibly good accept state, because it's sufficient that one of them is good. The automaton could reach it. Question?
I'm not quite following why you write in the other state S0, S1.
Okay, so the question is, why is this state here, and let's make it blue, S0, S1? Well, because this state indicates that at some point of the execution, my NFA could be either in state S0 or in state S1. This is in general, so you see, if I start from S0 and I read an A, Afterwards, I can be either in S0 or in S1. So the set of states that I can reach from S0 by reading an A contains two elements. This is not the same as, in general, as this. It's not the same. And actually, if you had two states like this, then you would have to decide, where do I go from S0 if I read an A? And then you would be non-deterministic. But you cannot be non-deterministic. You have to bundle up, you have to put together into a single state all of the possible places that you can reach by reading the A. You cannot have branching, because otherwise you're non-deterministic. You want to simulate all of the possibilities in a deterministic way. That's why I use the set as a data structure.
So if you're in this state over there where it's S0, S1, you can reach either S0 or S1.
No, you can reach both. Oh, so the question is, so if you're in that state, you can reach either S0 or S1 by looping. Well, actually, you have to think of this as a single state. And if you start in the state and you read an A, you go back to the same state. It just says, so if you were in S0 or in S1 before, by reading an A, you will still be in S0 or in S1 afterwards. Because this is so the collection of all the possibilities. So let's perhaps look at a slightly more complicated example. Yep, question.
Is it correct to assume that the set becomes a state in itself?
So the question is it correct to assume that the set becomes a state in itself? Absolutely. Absolutely. These two sets of states of the NFA are going to be the states of the DFA that we construct. That's why the construction, the algorithm is called the subset construction. The states of the DFA that you build are going to be, in general, all of the subsets of the set of states that you started from in the NFA. So if the original NFA had n states, how many states would the DFA that we spit out have? 2 to the n, exponentially bigger in the worst case. Okay, so there are 2 to the n possible subsets of a set that has n elements. Because for every element, you can decide, is it in or is it not? And that's a binary choice. You make n binary choices, and that's why you have 2 to the n possibilities. It's the same number as the collection of bit strings of length n. And there are 2 to the n of those. So let's look at another example before we actually do the construction in general. Okay, so let's take the collection. So I will not make it particularly big because otherwise we are really exponentially. Okay, so that's there are 3 states now. Let's see what happens. Okay, so our initial state, so that's my NFA. I want to use the subset construction to convert it on the fly into a DFA, which is equivalent to it. So how do I do it? Well, remember, the mantra is states in the DFA will be subsets of the set of states of the NFA. And the initial state will be the set that only contains the initial state of the NFA. So that's the initial state. And now we ask ourselves, okay, I am in S0 and I read an A. What is the set of all states that I could go to? S0, there's only one. So we look back. if I read a B, and I'm in S0, what is the set of all possible states that I could go to? Either in S0 or in S1. Okay, so far so good. But now we have to keep expanding our behavior starting from the state S0, S1. Okay, so if we read an A, where do we go? Okay, we have to look to remember all of the possible next states by collecting into a set all of the places that we could reach from S0 by doing an A, and all of the places that we could reach from S1 by doing an A. So what are these? S0, S2. Let me first draw it. So the question is, why S0? Well, you were in either in S0 or in S1. Okay? If you're in S0 and you read an A, you go back to S0. And that's the reason why you have S0 here. You have to record all the possible next states that you could reach by any of the states that are recorded in your set where you're currently residing. If you are in this state and you read a B, where do you go? S0, S1, or S2? Why? Let's see. So basically, if you are in S0 and you read two Bs in a row, afterwards you could be anywhere in your NFA. Why does this make sense? Look at the NFA. If you read two Bs from S0, you could take the loop twice, and then you're in S0. Or you take the loop once, and then you go to S1. That's the reason why S1 is in the set. Or you could just escape from S0 straight away and take the two Bs one after the other. Afterwards, you would be in S2. So this set here records the fact that from S0, if you read two Bs in a row, afterwards you could be anywhere in your original NFA. Okay? So let's keep expanding. Sooner or later we will finish. Okay? So if you are in S0, S2, and you read an A, where do you go afterwards? Okay, from S2 you can go nowhere. From S0, you can only go to S0. So back from where we started. If you are in S0, S2, and you read a B, where can you go? Okay, so let's see. From S0, you read the B, you can go to S0 or S1. From S2, if you read the B, can you go anywhere? No. So either you are in S0 or in S1. So we go back here. Now I think you can start to appreciate why NFAs are nice when you want to specify this language. Okay, so if you are anywhere and you read a B, where can you go afterwards? So if you are either S0 or S1 or S2 and you read the B, you can go anywhere actually. Because already from S0 and S1 you can go anywhere by reading a B. S2 doesn't matter because you can go nowhere. So you just have a self loop here. Do you agree? Because from S0 you can go to S0 or S1 by reading a B, and from S1 you can actually go to S2. S2 doesn't add anything because you cannot go anywhere from there. And in any event, even if you could go somewhere, these are all the states that there are. You cannot add any more. Okay? If you are in this state, S0, S1, S2, you're either in S0 or in S1 or in S2 when you read an A. You go to either to S0 or to S2. Fortunately, we had already seen that before. Okay, so that's the NFA. Well, that's the DFA, sorry. Woof. Well, not quite, because we need to decide where are the accept states. Now, the mantra is the following. You go through all the sets of states that you've generated. For each one of them, you ask, is there some accept state in there? If the answer is yes, you mark that as accept. Otherwise, you don't. So the only accept state in the original NFA was S2. So all of the states, all of the sets that have S2 in them are accept states. So this one and this one. Let me just use the check marks now because otherwise it gets a little bit messy. Where check mark means accept. Well, no, so the question is it only accepted in S2? It's accepted, remember now, your states are sets of states. So you accept in all of the sets that contain S2. Why does this make sense? Because if by reading your input string, you can reach one of the possible places that you can reach is S2, then this means the NFA would have accepted it because it would have processed the string and one of the possible places that it could have reached is the accept state, S2. That's why it's sufficient that one of the guys in your set is good. Because this means there is a way for me to process in the string right and reach that state. You also had bad ways of processing it right, processing the input string, but they don't matter. Because the acceptance condition for an NFA is if you have a way of doing it right, you will do it right. We don't care about failures. We only care about success. That's how you should think too. Sometimes we fail, but yeah, it's like the good goal scorers in football are not those who agonize about all the penalties that they miss. They only remember the ones they scored. And of course, I mean, how good you are, it depends on the percentage. But if you have a big ego, you say, okay, I missed 1 billion penalties, I'll score the next one. Yeah, fat luck. Okay, so basically that's the way to do it. That's how the algorithm processes. So what is the general pattern? Here's the general pattern. The input is an NFA. The output is a DFA. So let's say that this guy has S as a set of states. This guy will have the power set of S as set of states. Now, what is the power set of a set? Is the set of all subsets of that set. Discrete maths 1, or even earlier. Okay, the set of all sets of states in S. All of them. What is the start state? Well, this guy had S0 as start state. This guy will have the set that only contains S0 as start state. What are the accept states? Okay, so the NFA would have a collection F, which is a subset of S. This is the set of accept states. I'm about to scream, guys. This thing really wants me to scream. Okay? I'll turn into Pavarotti at some point. Okay, so what are the accept states in the DFA? They are all the subsets which have a non-empty intersection with the set of accept states, which means all of those that have some good guy in them. Okay, that's what we were doing before. Eh? Now, what about the transitions? So suppose that I have a set of states of the NFA. And now I want to ask myself, okay, where do I go to? When is it that from X, by reading an A, I go to some other state Y? What is this state Y? Well, this is the state that consists of all of the states that you could have reached in the NFA from some of the guys in capital X. So this thing is the union for all of the states in X of what? Of f of S of A. Now, recall, this thing here gives you the set of all of the states that you can reach when you are in the NFA, you are in state S, and you read an A. That's a set. And you union all of these sets together for each one of the states that you have in X, and you're done. I have to tell you, this is not easy today. It's not easy. Technology is great when it cooperates with you, but when it doesn't, it's not so great after all. Okay, so that's how it goes. For every NFA, you can build an equivalent DFA. And you can do that by using an algorithm. Which means you don't actually have to do it by hand. You just code the algorithm, and the algorithm will spit out the answer. Which is super cool if you're a computer scientist and somebody actually did the implementation for you. So the answer to the question that your colleague asked before is, no, magic does not buy you anything. Everything you can do with an NFA, you can also do equivalently with a DFA. But you know, in CS and in life, size matters. You have to pay a price sometimes. And what is the price? The price is that in general, in the worst case, the DFA that you build might be huge compared with the NFA that you actually started from. So sometimes you may have to wait a long time before your compiler spits out a fully grown DFA that is equivalent to the NFA that you gave it as input. And this is a proven fact. In general, we cannot do better than an exponential blowup. In the example that I gave you before, this didn't occur. Otherwise, I would not have been stupid by trying to build on the fly an exponentially big DFA equivalent to an NFA. That would have taken far too long. And you know, one of the hard guys, one of the hard examples for the compiler, it's something that we've already seen. It's this language that asks for all the strings which have a B at some position from the right. So if you have the language that consists of all the sequences of A's and B's with a B at the nth position from the right. We've seen several examples. Second position from the right, third position from the right, fourth position from the right. You can build a small NFA that accepts that language, where small means you need n+1 states. Remember what we did before? Let me try to find it. It was this one. 5 states for all the strings that have a B at the fourth position from the right. Yes? Sorry.
You say that the capacity of DFAs is much larger usually than NFAs, but isn't there computational time instead?
Okay. So your colleague is saying you're looking at the size of things, which has to do somehow with the memory consumption, how much memory you need to store these automata. But of course, there is also computational power. Sort of how long does it take to simulate the behavior of an automaton? In the case of an NFA, if you want to do the systematic simulation, then you will have an exponential blow up. Absolutely. Absolutely. So here we are just focusing on economy of description. Absolutely. So it's like when you're writing a program, perhaps in a programming language, you can write a given program in one line. Then in another programming language, which has different constructs, you perhaps need 84 lines to do the same thing. Which one would you use? The one perhaps where you can write it in one line, because we want to write efficiently. But this doesn't mean that the one-line program is as efficient as the 84 lines program. That's computation time. So there is a general pattern here. If instead of fourth position from the right, you said fifth position for the right, you just need to add another state. So in general, nth position from the right, the B, would need n+1 states. The loop here, and then the n states to count down. However, if you want to do this deterministically, you cannot do it with fewer than 2 to the n states. It's a proven fact. So what is the message? The message is that when you compare the expressive power of formalisms, and this is an example, DFAs versus NFAs, there are many possible answers you can get. Okay, all programming languages under the sky are equally powerful. They are as powerful as Turing machines, provided that you have you assume that you have unboundedly much memory. However, you probably prefer to program in Java or C++ than to program in Turing machine. You can try. Why? Because the fact that they have the same power doesn't mean that they are equally easy to use. It doesn't mean that they are equally efficient, which is important in computer science. It doesn't mean that they need the same amount of memory when they execute, which is also important in computer science. So computer scientists have many different ways of evaluating specification and programming formalisms. And each one of them is of interest in its own right. Depending on the comparison criteria that you use, you may have different answers as to how good or whether two formalisms are equally powerful or not. So in other words, there are many shades of gray. The world of computer science is not black or white. In fact, we are very colorful, so it's not just gray, it's pink, which is the new black anyway. And on this word of color hope, the sun is shining. Thank you very much for being here today, and I hope to see you on Tuesday.